All right, this is the second example of a motion graph that we're going to work through. All right, this one is a little bit different. This is called the Tower of Terror. It's actually an amusement park ride. I couldn't model it exactly, but this is somewhat close to what it does. Okay, the Tower of Terror is an amusement park ride that moves up and down. All right, so it starts on the ground, and that's said later in the problem. It starts on the ground, and it moves up and down and does some other things, and then comes back to the ground. But all of the motion is up and down, no side and side. All right, now it does tell us the horizontal axis is going to have a time unit of 2 seconds. So 2, 4, 6, 8, 10, 12. I'm going to label everything right off the bat. 16, 18, that's what we get for talking and writing at the same time. 24, 26, 28. So this is all time in seconds. All right. And then it does say that the vertical axis has units of 2 meters per second. So 2, 4, 6, 8, 10, and -2, -4, -6, -8, -10, -12, all the way down to -16. And this is in meters per second. This is velocity. Okay? So the first thing we need to recognize is that this is velocity versus time. So what we saw in the last graph isn't going to mean the same thing here because it's not position versus time. All right, one of the first things we recognize is that right here I've got a horizontal line. And remember, when I had position versus time, a horizontal line meant that it was staying in the same place. That's not the case anymore. This horizontal line means that it's moving at the same velocity, right? It means that for the first 6 seconds, it's moving 4 meters a second, right? It starts at rest right here, and then as soon as the ride starts, it goes immediately to 4 meters a second, and it raises at 4 meters a second for the first few seconds there. All right, for the first 6 seconds, and then all of a sudden it changes to go 10 meters a second. Right, so now it's going even faster. Right, so really what happens is it goes up slowly for 6 seconds, and then all of a sudden it's going up faster for the next 6 seconds, from 6 to 12, right? It's going 4 meters a second at first, and then all of a sudden it goes significantly faster, 10 meters a second, all right? And then, let's see, what happens next? It says next it's at right here. See this flat thing? That flat thing means, again, constant velocity, but it's a velocity of 0, so it's at rest from 12 to 14, right? It's not down at a 0 position. It had moved up and then moved up even more, so this is where it is from 12 to 14 seconds, all right? So we've started to get an idea of what's happening here. So let's go ahead and start answering some of the questions. The first question is, what speed does the ride travel for the first 6 seconds? So that's this guy right here. And we already said it's going 4 meters per second. All right, and what is the acceleration at 2 seconds? So the acceleration here, well, acceleration, remember, depends on the change in velocity. And right here, the velocity is the same for the whole first 6 seconds. So if the velocity is the same, then the acceleration is 0 meters per second squared, because the acceleration is not, the velocity is not changing, and acceleration defines a change in velocity. All right, now we go on to number 3, describe in words what happens in the first 14 seconds of the ride. Well, we actually already did that, right? We said it starts off slowly for the first 6 seconds, and then it goes fast, and it continues to go up for the next 6 seconds, and then for 2 seconds it's at rest at its maximum height there. And that's what happened in the first 14 seconds. And it says, how high did the ride travel in the first 14 seconds? Now this is a little bit harder, but we learned in one of our videos, and I'm going to remind you now, that to get the area, if you have a velocity versus time graph, okay, first we actually did slope, right? When we were finding this guy right here, the acceleration at 2 seconds, the slope was 0. The slope is the acceleration, right? How does velocity change over time? Your y-axis is velocity. So remember slope, you learned that in Algebra 1, it's the change in y over the change in x, the rise over the run. Well, the change in y is the change in the velocity, and the change in x is the change in time. That's your definition of acceleration. That's why slope is acceleration here. All right? So how high does the ride? Well, that's going to be the opposite, okay? The area under the graph is going to be the displacement. Now, what does that mean? That means, see right here, when I had this line right here, if I go from there down to the x-axis, you can see that creates kind of a rectangle. The area of that rectangle is the displacement that occurred during that time period. And you could kind of think about this, well, it's going 4 meters a second the whole time for 6 seconds. And many of you know that if you take the speed and multiply by the time, you get the distance. Well, that's essentially what we're doing. We're taking the height of this box, which is 4, I'm going to write it down here in the right left-hand corner, 4 meters per second. And then I'm going to multiply it by the width of the box, which is 6 seconds. And you'll notice that the seconds cancel out, leaving with 24 meters. So that's what happens right here in this first little box here. That is 24 meters. Now we're going to do the same thing right here. Okay, this guy has a height of 10 meters per second and a width of 6 meters. 6 seconds. Again, the seconds cancel out and we get 10 times 6, which is 60 meters. So this area right here, from that line down to the x-axis is 60. We add those two together and we get a total of 84 meters. So that's where I am up here. I am 84 meters above the ground, almost a football field up in the air. All right? Then it says what happens at T14. Well, that's this right here. What's happening there? Well, it was at rest, and then all of a sudden it has a negative velocity. It starts dropping. Okay, now notice that during that time, it has a constant slope. And slope here is the acceleration. So it has a constant acceleration downwards. It has a negative acceleration there, right? On the other side here, it has a positive acceleration. But for all of that time, all of this time here, the velocity is negative, which means it's moving down for all of this. Now, when it's moving down with a negative acceleration, it's speeding up. The velocity is getting larger in magnitude. But when it's got a negative velocity and a positive acceleration, then the velocity and acceleration are in opposite directions. That's what the sign is. Remember, the positive and negative is just a sign. If they're in opposite directions, then it starts to slow down. It gets closer to 0 meters per second. All right? So at t equals 18, approximately what is the velocity? And now here's where you have to be careful, all right, because it's tempting to want to find the slope, but we don't find the slope. It's at t equals 18, that's here. What is the velocity? And that's actually what I'm getting off of my graph here. The y value is the velocity. And so I'd probably say about negative 10.5 meters per second. That's the velocity at 18. Okay? Now, it does say that at 22, it's back at rest, right? Your velocity is back at 0 here, so it is at rest. Okay, how high is the ride at this point? We are going to need to do the same thing that we did earlier. Remember earlier, in order to find its height, we found the displacement by doing the area. The area was the displacement. We're going to want to do that same thing over here. We need to find the displacement during that time. Now, you'll notice that this shape is a triangle, right? So we're going to use a triangle to help us get the area. Now, my triangle, I'm going to use this as my base, and I'm going to find a perpendicular height here. because if the base and height are perpendicular, then the area is 1/2 base times height. So the area of that triangle will be 1/2 times the base, which went from 14 seconds to 22 seconds. So that's 8 seconds for the base. And then the height of that triangle is -16 meters per second. Now, notice you could have done this little triangle here first, and then that triangle over there next, and that would do the same thing. Okay, so if you weren't able to see the big triangle, don't worry about it. You can still break it up into pieces. You can even find the area of one square and count how many squares there are. That works too. All right, now we're going to do area equals 1/2 base times height. That's going to give us an area. You'll notice that if I do have a -16 as my height, because it went from 0 down to -16, then I'm going to get half of 16, which is 8, so I'm going to get -64, which means that my displacement, my change in position, is -64 meters. Well, it was at 84, so 84 minus 64, well, it's 20 meters in the air. So you can see that at this point it dropped down really fast. This is almost a free fall. And then it continues to drop, but starts to slow down, but we're not at the ground yet, right? We're still 20 meters up in the air. Now question 8 asks, does the ride end up back at the ground? Well, in order to find that, we're going to need to do the area of this triangle right here. What happens in these last 4 seconds? Well, you've got a base of 4 seconds and a height of -10 meters per second. And if we do our area there, if we do area equals 1/2 times the base of 4 seconds times the height of -10 meters per second, you'll notice that you get an area of -20 meters, which is our displacement. It was at 20, it dropped another 20, and so it ends up back at the ground. Yes, because total displacement equals 0. We had a positive 24, a positive 60, this was a -64, and this was a -20. You add all those displacements together, and you get a total displacement of 0, which means it had to start and end at the same place. The maximum magnitude of acceleration, well, that's wherever the line is the steepest, right? That would be right here. This is where the line is the steepest. Okay, and to find the value, I'm going to find the change in velocity, which it goes from 0 to -16. So acceleration is the change in velocity over the change in time. So I'm going to do the final, which is -16, minus the initial, and then divide by the time. That took 2 seconds. So I'm going to divide by 2, and that's going to give me a -8 meters per second squared, because this was meters per second on the top and seconds on the bottom, so I get -8 meters per second squared. So that is -8 meters per second squared. That's almost free fall. And where does it occur? Between 14 to 16 seconds. All right? And the maximum speed? Well, that's whenever the velocity has the largest magnitude, which is right here. The maximum speed is 16 meters per second, right? That's read directly off the graph, okay? So this can be a very challenging question when we start looking at velocity and trying to really interpret how velocity is different from displacement. But you can see that anytime it asked about speed, we just had to look at the y-axis. We didn't have to do a slope. The velocity versus time graph is great because we also get the acceleration and the displacement all from this same graph. And it's fairly straightforward to do those by using the slope and the displacement. So that's why velocity versus time graphs are pretty common. All right, that's it on this video. Go ahead and watch the next one if you'd like.